If it hadn't been for Dick's inspiration, many of the milestones on this plaque would not exist today. So I thank him for allowing me to learn from the people who I worked with on these. It's been a fun experience. It's become a hobby of mine. You can see how much I love this. I put this event together, so I just have a good time, and I hope you do too. We also have a special guest in our audience, Dr. Mohantesh Hiramov, who just became president of the American Society of Mechanical Engineers, or ASME. I invite him to come up here and just say a couple words. Is he around? Oh, he didn't show up. Okay, sorry about that. I also want to recognize some of the donors who helped create the wall behind us for allowing the plaques to exist. Besides Tom Coughlin and myself, donors include the Consultants Network of Silicon Valley, Eli Harari, Kevin Decker, Richard Williams, Steve Wozniak, Dave Patterson by way of UC Berkeley, the IEEE Foundation, and a very generous gift from Apple. So just a brief little bit about IEEE milestones. They recognize technical accomplishments that are at least 25 years old, and they're in the fields of electrical engineering and computer science. They started, or go back as far as Benjamin Franklin's work in 1751 about electricity, and also Marconi's experiments in wireless telegraphy, the transistor, the compact disc, and even the first stereophonic recording, which was done at Abbey Road Studios in 1931, long before the Beatles ever used that facility. A lot of people don't know that. And now onto our program about these Silicon Valley milestones. I remember coming to this building when I was doing consulting work in the 1990s, and at that time it was a Silicon Graphics building. And so in the wake of the dot-com bust in the early 2000s, with SGI's best days unfortunately behind it, the museum supporters were able to get this building for a virtual song. You know, many museums around the world have trouble staying relevant and staying active and really just staying in business. And you probably have seen some museums come and go, but they tend to be fairly static, or they don't really keep a dynamic environment, or they don't really bring people in continuously. This museum is the absolute opposite of that. It's dynamic. It has speakers on relevant topics. It has speakers on history that's fascinating. We have so much in this area. So this place is a unique place, and I'm very happy to be here today. Besides the numerous milestone dedications, this museum presents many programs on history, as I mentioned, and as such, it's really the go-to place here in the Valley for many different topics. While none of the plaques on this wall are IEEE milestone plaques, the very first one over to your right is actually what's called a special citation plaque. And this honors things that are not necessarily direct accomplishments, but they honor a place like the Computer History Museum. The first of these special citation plaques was installed at the Tesla Museum in Serbia. And it honored both Nikola Tesla as well as the exhibits in that building. The second special citation was dedicated here at the museum in 2015, right over here. And one will be dedicated next month at the Heinz Nixdorf Museum in Germany. So that will be the third special citation. Today, I'm happy to have the museum president and CEO, Daniel Lewin, with us. You know, talk directly about this special citation plaque and what it represents. Now, Daniel has a long history in the tech world, including at Microsoft, Apple, Next, Go, and Sony. Daniel is the guy with the bright smile and the upbeat attitude that brings people into this place. He gives you a welcome, and you know he means it. He's a good guy. And it's my pleasure to invite him to the stage.
Well, welcome everyone to CHM. And thank you, Brian, and thank all of you for what you've done and the fact that you're here and out and about on a day like today. It is a memorial and memorable moment in time. And I think, you know, we'll all reflect on this day for various reasons. I'm very, very pleased to be here. And some of you I know, I've recognized a number of faces and have had a chance to chat with a few folks. I thought I would spend just a moment explaining a little bit about who I am and why I'm here and what we're doing with the museum. And in fact, without the partnership Brian and Uday and the rest who've been helping organize a lot of these programs, we wouldn't exist. So it is the community and the stories and the participation of people like you that make a difference and keep this museum alive. I thought I'd start by making the point that I wouldn't be here if it wasn't for a person, and this person's name was Miss Kirkwood. And she was my second grade teacher. She taught me binary in second grade. And that was a long time ago. If you fast forward a little bit, when I was in high school, I had a chemistry teacher that organized the chemistry chapters on punch cards so that we could select chapter 1 and do the Q&A on every question that had been asked and answered on the state regents exam in the state of New York. So I started to use punch cards when I was in 11th grade. And there we go. I didn't get to use computers until much later. But while I thought I was good at math, I ended up at Princeton, and I realized I was not a mathematician very, very quickly. When I left school, I came to Silicon Valley on a bet with a family member. And the two people that I met when I arrived owned a home on the top of a hill off of Arrastradero here in Los Altos Hills. And one of them is a guy named Cordell Green, who's won the Grace Hopper Award for the understanding the theoretical basis for the field of logic programming. And the other one was a woman named Peggy Karp, who was working on the domain name services, the internet naming conventions. Those are the first two people I met when I moved to Palo Alto. So I didn't leave. Understanding binary helped. Meeting people like that and people like you made all the difference in my life. And it's landed me here at CHM in the last 3 years as the CEO since I retired from Microsoft. The last time I was deeply involved in a project that had anything to do with semiconductors and logic, I was one of the founders at Next. I worked on the Mac. There were 10 of us in the beginning. When I left Apple, I went to work with Steve Jobs and 4 others, and we started a company called Next. We did this giant project. It was a 25,000 gate array. There was one company in the world that could fabricate the chip at the time. It was Fujitsu. That's the last time I was anywhere near what's happening today as a result of the tools and the commitment of all of you who participate in the creation of this amazing world that is Silicon Valley. And it's the core of this industry. And as one of the most famous, there are many famous people here for all sorts of reasons, but one of the most famous obviously is Gordon Moore. I did get to meet Gordon, and he followed a guy named Grady Booch, who used to be a trustee at the museum, who defined the uniform modeling language for programming. And he was going on and on about the importance of software. And when Gordon got up and spoke, he said, software is really interesting, but it has to run on something. So I'm here at CHM because we have a challenge before us. And we call it the Computer History Museum. But CHM could also stand for Computing, Humanity, and Meaning. And I say that because life as we know it doesn't exist without computing. So at the museum, we're using the lens of asking that question and pulling from our inventory and our archive as we move forward into a world of digital twins and full programmability of this museum, which is where we're headed. We're moving on into the world where life as we know it doesn't exist without computing. And it's a result of all the work and the partnerships that have come about over the years that is causing us to reflect on this moment in time. And I think, again, today is a day for reflection, and the genius that's gone behind the tool set that we're celebrating today is fundamentally important. And it is, again, my pleasure to be here, to welcome you to the museum, to let you know that we're on a path, and it'll take us years to achieve. But all good things take time. So again, thank you, Brian. Thanks all of you for coming. We appreciate your support, and enjoy the museum as you can when we reopen. Thanks. Bye-bye.
Thank you, Daniel. So the second plaque on the wall here is for Shaky the Robot, which was a project at SRI in Menlo Park that took place from 1966 to 72. And the milestone was dedicated here in 2017. While that plaque is actually mounted in the lobby of SRI, I had thought it would be a good idea to have a duplicate plaque mounted next to the one and only Shaky, which is here in the museum. And it's the centerpiece of the artificial intelligence and robotics part of the museum. The museum board decided a better place would be here on the wall. And as it turns out, that ended up opening up a lot of possibilities. And in fact, you see them right in front of you. So I purchased that plaque and they put it here. And then one thing led to another, and we've got a lot of plaques here. So I thought that was a pretty interesting sequence of events. Now, Shaky was an ARPA-funded project that broke ground in numerous areas, including robotics, AI, and computer vision. And when SRI proposed it to ARPA in the mid-1960s, they called it a mobile automaton for reconnaissance, i.e. a robot. But they couldn't tell ARPA they wanted to build a robot because that would be like asking them to help them with a science fiction movie. So they had to kind of mask the idea, but it ended up being incredibly successful. And its foundational algorithms are used throughout the world today. They help compute your driving directions, for example, with Google Maps, the paths of characters in video games, and even the paths of the Mars rovers. They're foundational to the stay-in-lane technology used in millions of automobiles right now. And Shaky's been called the great-grandfather of self-driving cars and military drones. Today, I welcome Peter Hart, who's one of the world's most cited robotics authors, and also a fellow of the IEEE, ACM, and the Association for the Advancement of Artificial Intelligence. I had the pleasure of working with Peter to craft the proposal for Shaky, and that was really a pretty easy feat because he handed me what was effectively a scientific paper describing Shaky. And it just was very easy. It only took about 3 or 4 months to get this approved, which is like people sometimes take 2 or 3 years. So thanks to Peter, it was a very easy task, and I welcome him to the stage.
Well, thank you, Brian. Can you hear me? It's okay? Well, thank you, Brian, for that very generous introduction, and welcome and good afternoon, everybody. I imagine everybody here has been in the museum, and so I suppose you might be wondering, Shaky's not that much to look at. What could it actually do? So I'd like to tell you what Shaky could do. So Shaky could perceive its surroundings. It could autonomously navigate from place to place. It used mathematical logic to derive facts that were not explicitly present in its world model. It created its own plans to solve problems for which it had no pre-programmed solution. It continually monitored the real-time execution of its plans, and it took corrective action if things were not going according to plan. And over time, it improved its problem-solving ability through learning. It communicated with people in a simple form of English. And Shaky did that 50 years ago, running on a computer that filled a machine room and had 1 megabyte of memory. Now, Brian's mentioned that some of the algorithms that we invented for Shaky are in widespread use today. But that's not the reason, or at least not the main reason, that Shaky is important. I think the main reason that Shaky is important is because it proved that robots and intelligent robots were possible. You have to remember that until Shaky, robots existed only in science fiction. They were literally fantasies. Shaky proved that the fantasy could be made real, and in doing so, kicked off the field of robotics. Thank you.
Thank you. Beautifully put. If you want to have a feeling for what shaky looks like, there's a poster from the dedication event from 4 years ago posted right behind you on the brick wall. You can see that blue figure. That's kind of a 1960s Fillmore kind of a poster, shall we say, because it was from that era. But it does show what shaky looked like, which was really a fascinating project. The third plaque on the wall behind us is for Doug Engelbart's famous demo, which took place in San Francisco on December 9th, 1968. It's often called the mother of all demos, and it showcased many technologies that would become ubiquitous, including hypertext, video conferencing, and perhaps most memorably, the mouse. Like Shaky, Doug's demo was an SRI project, and this milestone was dedicated here at the museum a few weeks after the Shaky milestone. I assisted Mark Weber with this milestone's dedication, and now Mark is the curatorial director of the Internet History Program here at the museum, and he organized the Engelbart Symposium, and he also helped introduce Doug to the web community back in the 1990s. Mark will provide a few words about his perspective of the impact of Doug Engelbart's famous demo.
Okay. Testing. All right. Thank you, Brian. Oh.
Oh, can you use it?
Does that work? Testing. All right. I have my notes on it. That's the only. It is on airplane. I put it on airplane mode. Thank you, Brian. 5 years ago, I was honored to help commemorate the mother of all demos as part of the IEEE Milestone program and to celebrate the people in the ARC laboratory who made it happen. I want to thank Brian and Dick Ahrens, who's here, and Shane Hodge. And as well as remembering Doug, I would like to especially remember Bill English, who made so much of the original demo happen. Today, we spend far too many hours at the kind of interactive screens Doug Engelbart demonstrated in 1968. As he foresaw, we do much of our reading, writing, and research online. We click on the hypertext links he developed using the mouse he co-invented. We chat and we share documents and send emails as his team did back then. We do all of this over computer networks, including the internet, both partly developed within his lab at SRI with a NIC. But when it comes to the kind of knowledge navigation and collaboration tools, the heart of Doug's NLS system, we've climbed only the first rung of the ladder. The same is true when it comes to the daunting goals that drove him to build all of his technology, to augment human intellect so that we might better address the world's big problems. Are those unbuilt portions of his vision useful? If so, is it too late to incorporate them into an online world that is already largely built? So these are the kind of questions that we addressed in the symposium and in other forums. They're even more relevant today as COVID has driven yet more of our lives online. So I first met Doug when my colleague Kevin Hughes and I interviewed him in 1996. And as Brian alluded to, we were very proud when he agreed to keynote and demo NLS at the Web History events back in 1997 at the International Web Conference. And one of our main goals at the time was to introduce the original online pioneers to the web community, especially the young engineers who were building things, but often had little idea of what had come before. And those efforts eventually led to the Internet History Program here. The main records of Doug's work are split between the museum with the ARC NIC collection that was saved by Jake Feinler and Stanford Libraries. And to offer or suggest other relevant historical materials, please see our website or get in touch with me, Weber@computerhistory.org. And thank you. It's an honor.
Thank you very much, Mark. So I'm going to move over here now because I want to be able to have each of our speakers in the same frame as the plaque. So our next plaque here is the fourth plaque, and it honors the early work done by Eli Harari when he was employed at Hughes Electronics in the 1970s. Through experimentation in a laboratory, Eli showed that thin silicon dioxide films of about 100 angstroms were an efficient and reliable electron conduction mechanisms for both program and erase, and in fact allowed for the electrically erasable floating gate EEPROM in 1976. This important discovery was also foundation to the subsequent success of flash memory, which in 2020 grew to a $56 billion per year industry. It's likely that every person here, as well as in our online audience, has a cell phone, and its ability to store and run apps and also to take photos relies on flash memory, whose phenomenal success has its roots in the work Eli did back in the 1970s. Eli founded the phenomenally successful company SanDisk in 1988, and I started working with him on my first milestone back in 2010, which was dedicated here at the museum in 2012. Eli Harari, please present your thoughts on your milestone.
Thank you, Brian. Yeah, so yeah, this is a great honor, obviously. So just to take you back a little bit into 1975 or so, at that time, if you were trying to store a program for your computer, it was, of course, the EEPROM. Dov Furman-Minkowski at Intel invented the EEPROM. You could write a program into that. It would keep it. If you wanted to change a program, erase it, you needed to put it under an ultraviolet lamp for 15 minutes, and it erased the whole thing. So there were a number of people at the time that were trying to go from EEPROM stands for electrically programmable read-only memory. There was a lot of people working on finding a way to put a second E, electrically erasable, programmable, read-only memory. And I was just lucky in that during my PhD work, I came across the quantum mechanical effect that's called Fowler-Nordheim tunneling. In 1975, very few people have ever heard of Fowler-Nordheim tunneling, but it was a way that you could allow an insulator, glass, SiO2, to actually conduct electricity. So, so I came across the idea of using Fowler-Nordheim tunneling. The problem was, in 1975, the MOS transistors at that time were very, very rudimentary, and the gate oxide was about 1,000 angstroms. So in order to get Fowler-Nordheim tunneling through 1,000 angstroms of silicon dioxide, you needed close to 100 volts, which was totally impractical. So I came up with the idea, okay, in order to get to 10 volts instead of 100 volts, I need to make the silicon dioxide 10 times thinner, going from 1,000 angstroms to 100 angstroms. That's like 10 nanometers. That even today is quite thin. But there was nobody that has ever known or even thought about 100 angstrom MOS transistor. So I could prove the concept at Hughes. We had a very lovely lab. I could prove it, in fact, very, very quickly. I showed that I could not only erase, but I also program it. But the key then, the next 2 years at Hughes, and I had tremendous facilities and tremendous support from Hughes to actually do all the physics of that thin film oxide, and to prove, in fact, that we could manufacture it reliably, reproducibly, and achieve over 1 million times program erase, good endurance. And that really was what made this technology viable to be the replacement for EEPROM, and later on, really the foundation physics. Today, not today, yeah. Today, Fowler-Nordheim, of course, is used for program and erase most non-flash transistors. But of course, at the time, we never thought that this would go that far. And indeed, now, think about your iPhone, indeed, without memory, because the only memory that works there is very low power, battery operated storage. And when I started SanDisk, the idea was use this to develop really a memory that could be reliable, but very, very high density, very low power. And that required really a system solution because one of the consequences of this technology of programming and erase is that you wear out that thin oxide, you wear it out, and eventually it's dead, it dies. And the physics is very clear, very, very clear. So I knew that for storing data as opposed to storing code, you really needed to have a system solution that anticipated that every single cell, and we're talking about millions, and today we're talking about trillions on a chip, trillion transistors, you needed to have a system that treated every cell in its own right. So, you know, I could not have been luckier than this. Everything kind of fell into place way more than I ever expected. And unfortunately today, you know, there's not too much silicon going on in Silicon Valley. So I really do hope that this latest, you know, Pat Gelsinger at Intel and a lot of, you know, the government support into our industry to bring back semiconductor technology manufacturing. We're talking about starting from the basic cell, the basic transistor, and building it into a chip and then into a system. And that's really, it's just very, I'm the luckiest guy.
Thank you very much. In the early 1980s, UC Berkeley Professor Dave Patterson successfully proved the merits of a streamlined processor architecture called RISC, which stands for Reduced Instruction Set Computing. But there's much controversy in the industry for many years about this approach. By the mid-1980s, Sun Microsystems had become a successful company selling Unix-based computers, but they wanted to differentiate their product with higher performance. Based on its faith that RISC could propel its success, Sun hired Professor Patterson as a consultant to assist with the design of a new processor chip. This bold step proved very successful and allowed Sun to become the dominant platform empowering the internet's dramatic growth for many years. You may remember Sun's slogan from that era, "We are the dot in .com." That was based on their SPARC architecture. I earlier noted that all your cell phones use flash memory. I can add that likely every one of your cell phones also incorporates RISC architecture. Uday Kapoor managed a team that designed SPARC, which was the first commercial success for this RISC architecture. Uday is here with us today to talk briefly about the RISC and SPARC milestones, which are the 5th and the 6th milestones on this wall. Uday.
Hello. Actually, I'm really privileged because I'm an active volunteer at the museum, and Daniel and I, we work together on a lot of things. And so it's so nice to be here. I'm so privileged to be with all of you. And I think you've already given a little background. So I'm covering 2 milestones here. One is the Berkeley RISC, and the other one is the SPARC. Okay, not sure. I actually turned my cell phone off. So it so happened that actually I was happily working at Intel designing microprocessors when I was approached by TJ Rogers to come and look at an opportunity to work with Sun on the first RISC processor. And so I was not convinced, but he spent about 3 hours with me, and because I was pretty happy at Intel. But he did convince me, and I then moved and started this team working with the Sun team and put that team together to do the first Spark chip. And that was actually previously proven by a gate array, and Ellie and I have worked together also in the past. So Ellie, you mentioned Fujitsu. Fujitsu gate arrays have always been the standard, and so it was proven by Fujitsu gate array. But so the chip came out and it worked pretty well. It was targeted to work at 33 megahertz, but it was proven at 50 megahertz. So we had a great team, and so that became the first, Spark processor. And looking at the wafer here, I actually retired from Sun Oracle, and this is the wafer and the chip, which is almost the last processor that was done. It's M8, which has 5 gigahertz speed and has 10 plus billion transistors and has met the highest performance. So even at late as recently, it was still the highest performance chip. So, so that going back to what you said, I think the thing was proven at Berkeley. Berkeley RISC was really what, and it was a privilege to work with Dave Patterson. And when I was approached by Dick Ahrens to propose this milestone, I immediately suggested that we need to consult with Berkeley. And so Professor Hodges and I coordinated creating the two milestones together. And in fact, they were celebrated together. I was at Berkeley with Dave Patterson, and then Dave came over the next day when we celebrated the thing, and I think you were there. And we have a poster, it actually fell down from the wall, which was there at the event. So again, so this is about the milestone. So thank you very much.
Thank you very much, Uday. Our 7th plaque on the wall is for Moore's Law. The name eventually applied to Gordon Moore's 1965 prediction at Fairchild that the number of components on an integrated circuit would increase exponentially with time, allowing costs to decrease. Silicon Valley's phenomenal growth was propelled by entrepreneurs who assumed Moore's Law would continually lower costs, thereby allowing products to be attractively priced by the time they came to market. A very key enabler of the success of Silicon Valley. Now, Gordon Moore is now 92 years old and does not travel much, but our next two speakers worked with Gordon at Intel. Ted Hoff is one of the 3 designers of the Intel 4004 microprocessor. It was the first processor incorporated onto a single chip. I work with David Laws of the museum here, along with Ted Hoff, Federico Fagin, and Stan Mazer on a milestone for the 4004. The plan was to dedicate that this coming November, but of course those plans have had to be put off. However, Intel has promised that they will purchase a duplicate plaque that we can put on the wall for the 4004. And that will, the initial plaque will be at the Intel Museum in Santa Clara. I now invite Ted Hoff to talk about some of his memories of Gordon Moore.
Thank you. Thank you. Intel was started around September of 1968. That's when the company opened for business. In the early days, at one point, Gordon Moore invited me to come to his office, and he showed me this article that he had published a few years before. And in it, it showed how the number of components on an integrated circuit had been increasing over time, roughly doubling every year to 2 years. And by this time, Intel had a couple of products that were on the drawing board and had an idea of how many transistors each would have. And when you looked at his chart, those parts were actually above the line. So Intel was going to be aggressive. In fact, Gordon's main focus was on this whole idea of processing and how silicon behaves. And one of the things he also showed me were yield curves. And the idea was, how does the yield of an integrated circuit vary with the size of that circuit? Now, you'd normally affect if defects were uniformly distributed and you had a chip that was yielding, let's say, 10%, and you doubled its size, you'd expect the yield to go to 1%. But it didn't drop that fast, and Gordon explained the reason was that the defects are not uniformly distributed. Now, of course, Intel was, the main players were Bob Noyce, Gordon Moore, and Andy Grove. And they were quite different people. And to give an idea, Gordon is the type who, you might say, played his cards close to his chest. And at one point, the IEEE had a meeting at one of the local hotels, and Gordon was on a panel at that meeting. Somebody in the audience asked Gordon, he said, I see Intel is doing something with silicon nitride. Can you tell me about that? And Gordon said, sure. We use just the amount to get the effect we're looking for. Now, didn't really give much information. Now, suppose it had been Bob Noyce who was on the panel. He would have been much more open and said, we tried it, it didn't work, we don't use it. That number that Gordon hadn't quoted was 0. Now, on the other hand, suppose it had been Andy Grove who had been on the panel. His answer would have been more like, it is none of your, and you can fill in a few expletives here, business. So these three very different men worked together to make what I think was a remarkable company. Thank you.
Thank you, Ted. That story tells you so much. I love that. Thank you very, very much. Short and sweet and to the point. Our 8th plaque here is for the birthplace of Silicon Valley, which was a humble one-story building at the corner of San Antonio Road and California Avenue, about 3 miles from us here. That's the site of Shockley Laboratory, where silicon semiconductor devices were first produced in this area. Like Ted Hoff, Federico worked on the Intel 4004. The critical importance of Federico Fagin's role in the success is often not appreciated, however. He developed enhancements to the metal oxide silicon, or MOS, transistor technology that delivered 3 to 5 times faster speed in half the chip area of conventional MOS. This critical work is what allowed the 4004's 2300 transistors to be fabricated on a single chip, a dramatic first step for this critical component that is now used universally. Federico was born in Italy and worked for Olivetti before coming to America, and then working for Fairchild and Intel, and later forming Zilog. He'll provide his perspective on what Silicon Valley has brought to the world. Federico.
Thank you. Should I go where the plaque is? All right, it's a pleasure to be here and telling you that in 1956 in San Antonio Road in Mountain View, the door opened on Shockley Semiconductor. Shockley is the one that put the silicon in Silicon Valley, because his idea was to create transistors using silicon instead of germanium. At that time, germanium was the material, the element that was used for almost all transistors built, and silicon was much better. So Shockley assembled about 12 of the best engineers and scientists that he collected throughout the US, brought them here, and about a year later, 8 of them left in mass to start Fairchild Semiconductor, which of course you have heard, because Fairchild has 2 distinctions. One, it was the first startup that spawned several hundred other startups out of itself in many generations. But perhaps more importantly, was the one that created the planar process to make integrated circuits. The planar process was initially meant to create transistors by making many of them at once using photolithography, when before transistors were done one at a time. The inventor of this technology was Jean Herny. Is a Swiss engineer who was one of the 8 co-founders of Fairchild. And that technology, excuse me? No, that was Jean Herny. And so this technology then, a step forward from that technology was to connect those transistors that were already in the surface of the single crystal silicon. So that became the integrated circuit. The first one was sold in 1962. And at that time, all the integrated circuits used bipolar technology, and MOS technology was a sort of a kind of a sidekick, so to speak. It was not a very interesting because it was very slow and it was unreliable, and so it was kind of big boys use bipolar, and I when I found out about MOS was in 1964 when I was still at university, and then I came here in 1956 to 1966. I'm getting old, so so in 1964 I found out about MOS for the first time. And in 1966, I came here to take a course on MOS technology at GME. General Microelectronics was the first company to make integrated circuits in the world. It was one of the startups that came out of Fairchild. And I didn't know that I would have come back here in '68 to work for Fairchild, where I was the developer and the person in charge of the silicon gate technology, which is the technology that was able to produce 5 times the speed, twice the density, better than 100 times less leakage. It had all the characteristics that allowed to make all the missing ingredients, which were dynamic memories, because you couldn't make dynamic memories if you had too much leakage, the microprocessor, the CCD, and the floating gate transistors that were done all at Intel. So Silicon Valley really is what it is because of silicon. And I'm sorry that the silicon is disappearing from Silicon Valley, but actually, much of the design of systems is done here. And I hope that the silicon will come back, because silicon is fundamental in the new era of information, just like oil was fundamental in the industrial era. So long live Silicon Valley, and I'm happy to be part of this great adventure.
Thank you, Federico. If you want to learn more about it, I just received this book from him. It's quite looking forward to reading that. Now, one person who was originally on our program was Steve Wozniak. Very sadly, his father-in-law just passed away, so he's in the Midwest right now. I was amazed to hear he had actually planned to rent a jet to fly him out here for this event and fly him back. However, his family called, so he has his priorities, so I very much respect him for that. Tom Coughlin and I worked on 3 milestones for Apple, as he noted a little bit earlier, the Apple I, Apple II, and Macintosh. Tom worked most closely with Steve, and I worked most closely with the Macintosh team. In that process, I gained a greater appreciation for Steve's ingenuity and I added some embellishments to the Apple II proposal to reflect some of this work. I'll give just one example about that I think is highly reflective of the genius of Steve Wozniak. In 1977, the first Apple II came equipped with a cassette drive for data storage. You can imagine how clunky that was. However, in 1978, Apple introduced the Disk 2, a 5¼ inch floppy drive with an expansion slot controller. Basically, it replaced the cassette drive as the medium of choice for that Apple II. Now, this was a design marvel of Steve Wozniak's in that it used just 6 low-cost chips as compared to literally dozens of chips used in other floppy disk controllers of the time. The 6 chips required special software that was included in the Apple DOS operating system in order to perform all the operations necessary to fully support a floppy disk drive. The update increased Apple II sales dramatically. Were it not for Woz's ingenuity with that device that gave new life to the Apple II product, Apple may very well have fallen by the wayside and you wouldn't know its name barely today. Steve's design evolved into the single chip integrated floppy controller called the integrated Woz machine that's used in the Macintosh. And Ron Nicholson is with us today, and he worked on that aspect of the Mac. Ron, could you raise your hand, please? Yep. Thank you. Also with us are 2 other Mac designers, Rich Williams and Martin Haberly. Could they raise their hands too, please? Yeah. So I worked with these folks and about 40 others on various aspects of the Macintosh proposal, and it was a very, very interesting process. So bronze plaques for the Apple I, Apple II, and Macintosh will soon be installed on this brick wall right over here, and there'll be a formal dedication at some point in the near future. Our 9th plaque is for the Dialog online search system. Dialog was the subject of the Stanford PhD thesis of our next speaker, Roger Summit. Roger conceived and productized Dialog at Lockheed and then managed it after it was being spun off as a separate company. Its powerful search tool is still in active use today. You may wonder how it can compete with Google, but Dialog meets the needs of a set of customers that include pharmaceutical companies that perform studies of new drugs, the U.S. Patent Office in its searches for prior art, and many entities that need access to highly vetted technical studies and documents not found on the web. Also, from the outset, Dialog had the ability to perform iterative refinement of its search results, something not easily done even in today's search engines. So if you use Dialog and you found a bunch of hits, and you knew you had some good stuff in there, you could refine that search very easily. A very critical design aspect from the outset of Dialog. I worked with Roger in composing the proposal for this milestone that was dedicated in 2019. I also had the pleasure of assisting our earlier speaker, Mark Weber, with the oral history of Roger in this past June. Roger will now provide his thoughts about Dialog. Roger.
Well, I'm honored to be able to speak about Dialog, which is a software product among all of these hardware specialists that we've heard from earlier today. But what I'd like to start with is to take you back to 1980, 85, in the 80s, and have you recall how you accessed information in those days. If you had a curiosity, where did you go to find an answer? Well, many times you simply gave up. Other times you could go to the library and access some very large books and maybe find subjects oriented by subject matter, but it was very hard to do specific searching in those days. Okay, in the early, let's see, did I say 80s? I really meant 50s. I really meant 1950. Woo! I got behind myself. So let's now we'll move up into the beginning of the 60s, and there were computers around in those days. They were second generation computers. We called them batch computers because there was no human interaction to speak of. It was all tape in, tape out, and printer output. And there were search systems going at that time, that were batch systems, but they were very awkward because you punched up your search on punch cards. It was batched along with a number of other searched and then ran against a tape containing the documents that were involved that might be of interest to you. I ran into that kind of thing in the late 80s in school at Stanford when we were looking at information retrieval processes. We had meetings, industry meetings, and meetings with IBM. I met an H. Peter Lund, who was an IBM visionary who invented the quick index, keyword in context index, that allowed you then to rotate titles of documents and be able to search on the title of a document or title words in a document. But that was still very cumbersome. So when the third generation technology came along, that is the 360, IBM 360 technology, I saw the chance that we could leapfrog all over the batch search systems because of what that technology provided, which was telecommunications, mass random access storage, and human interactivity via terminal systems. I made a proposal to Lockheed Management to set up something called the Information Sciences Laboratory, which we did in Stanford Industrial Park. And we got one of the very early IBM 360 machines in, let's see, it was announced in '64. We got it in '65 and set it up in the lab. And I started work on information retrieval. Now, I visualized information retrieval as a process, not a probe. And when you search today, it's usually a probe. You get your output, you reformulate your search, you go back in. With a process, I visualized the database as an information space so that when you did a search, you built a subset of that space, but you might want to use that subset later. So we saved the subsets and allowed people to intersect subsequent sets with prior sets in order to refine a search or to elaborate on that search. We were lucky enough to win a NASA contract in 1967, which led to our business. And the business, we went commercial in 1972. We established a network for SRO in Europe, the first information retrieval network in Europe, and went on from there. And that kind of activity is what resulted in the milestone that I worked with Brian on. Thank you, Brian.
Thank you very much, Roger. Pleasure having you here. Our last speaker is Larry Nagel, who's been a member of our IEEE Consultants Network for over 10 years, including our chair from 2010 to 11. Larry created the SPICE circuit simulation program during his years at UC Berkeley while he was working on his master's and his PhD from 1970 to 74. I always like to tell the story that when Larry first attended one of our Consultants Network meetings and introduced himself with regard to his work on SPICE, he got an immediate round of applause. Many of our members have used this product and it's still in active use today. Kind of blows Larry's mind thinking after all these years, people are still using software based on his original design. SPICE originated from a graduate class project, and the 1970 version included an innovative scheme for handling sparse matrices. Wide exposure from the 1973 conference led to many requests for Larry's source code, which UC Berkeley distributed to the world on 9-track tapes. SPICE was thus quite likely the first successful open source software product around the world and was started using Larry's code as the starting point for many different projects. The code consists of 8,000 lines of Fortran 4 statements, which resided in 40K words of core memory, and was originally entered on punch cards. SPICE and Moore's Law worked hand in hand as transistor counts continued to increase, since circuit simulation of the ever-increasing complexity of new chips was essential before the chips were fabricated. SPICE remains the basic of IC simulation tools to this day. With that, I invite Larry to come and tell us what's underneath this mysterious blue velvet draping. So we're going to go over to something or other here, and we're going to have our dramatic dedication of this duplicate plaque. This is about 11 years after the original dedication here at the museum. So Larry, I present you with the duplicate SPICE circuit simulation milestone plaque. Now the words on this plaque read SPICE, meaning Simulation Program with Integrated Circuit Emphasis, was created at UC Berkeley as a class project in 1969 to 70. It evolved to become the worldwide standard integrated circuit simulator. SPICE has been used to train many students in the intricacies of circuit simulation. SPICE and its descendants have become essential tools employed by virtually all integrated circuit designers. Now, Larry, would you like to share your thoughts?
First of all, I'd like to express my sincere appreciation to Brian and all of his helpers, but especially to Brian for pulling this off. I know it was a tremendous amount of work. Thank you, Brian. Thank you very much. And I would also like to just mention that I stand in awe, being the 9th speaker after all of the giants of the industry that just got up and spoke about what they've done in the industry. And it's an amazing presentation to have that many people in the same place at the same time talking about how they literally built an industry out of basically apricot orchards. So it's amazing. I would like to give just a few stories about SPICE, which probably some of you have heard before and some haven't. I'd like to point out that each of these plaques represents a milestone, an achievement that was realized by a team, a hardworking team of people, not just one individual. This isn't really a hall of fame like they have in Canton, Ohio. It's teamwork, and SPICE is especially that. I'm the one who's talking about it, but what we're really talking about is an achievement that was done at UC Berkeley over many, many years, and involving many, many people, too numerous to mention at this point. However, I would like to say its very early origin of SPICE is a fascinating story. It's attributable to Professor Ronald Rohr, who was a brilliant engineer, a professor at Berkeley, and his specialty really was more circuit theory, but he got involved in circuit design as well. And while Ron was a brilliant engineer, he's also as well known as being a very innovative educator, always willing to try something new to get students interested and to get students involved in their own education rather than just sitting in a chair taking notes and then putting the notes back on a final at the end of the quarter. So that said, Ron took over a series of classes on circuit theory in the school year 1969-1970, and those courses were supposed to be circuit synthesis and this sort of thing, and I decided to take it because I figured you can never know too much about circuit synthesis. I don't know how many of you even know what circuit synthesis is, but it's a way of generating circuits methodically. So Ron walked in the first day of class and said, this isn't going to be a class on circuit synthesis. This is going to be a class on circuit simulation. You folks are going to learn circuit simulation by writing a circuit simulator. And if the person that will be the judge of how well the simulator works will be Don Peterson. If he likes it, you'll all get an A. If he doesn't like it, you'll all fail the class. I mentioned motivating students. Well, half of the students immediately got up and walked out the door, which I guess was predictable. The other half, including me, said, wow, I don't know what I'm getting into here, but it sounds like it's going to be fun. And so for the next 3 quarters, we took a class. The first class was a program that could do DC analysis. The next class was the next quarter was we extended that to AC analysis, and then finally we extended it to transient analysis. Now, a little more context. The machine that we had was sort of the poor stepsister to the 6600 up on the hill at Lawrence Radiation Laboratory, which was at the time the most powerful computer available. The 6400 was a little less powerful, but it's still a very powerful machine. It had the input, of course, was punch cards. The output was a line printer. It had all of 120,000 octal 60-bit words memory. That translates approximately to 256 kilobytes. It had no disk. It had disk, but not that we could get at, not that we could use for anything. So that was what we had to work with, and that was in 1969. That was one of the most powerful computers in the world. The circuits that we were interested in designing and that we were interested in simulating, the benchmark circuit was the Fairchild UA741 op-amp. It had about 25 transistors in it, 28 transistors, something like that. And our goal was to be able to do a AC, DC, and transient simulation of a 741 op-amp with the computing resources we had. And a lot of people said, oh, you'll never be able to do that, because at the time, the simulators we had were able to handle about 6 to 10 to 12, maybe 12 transistors, and that was it. So SPICE wasn't the first program that was written at Berkeley. So it's not really the first open source program, because we did have a program called BIAS, and we had, which did DC analysis only, and we had a program called SLIC, which computed the poles and zeros of a linear network. But SPICE was the first one that could do AC, DC, and transient all in one package. So the team that was taking these classes set off to try to conquer this kind of incredible goal. And we introduced a lot of new things, as you would expect from Ron Rohr. One of the things we did was we were, I think, the first program that actually utilized sparse matrices to simulate the circuit. And that reduced the amount of computing power required from n cubed to n to the 1.2 or something like that, where n is the number of nodes in the circuit. And it made 100 nodes a realizable goal, even though none of the other simulators available from universities or from public could do that. It had built-in models like BIAS and Sync did. And of course, this was a bipolar only house. The 741 was bipolars only. It wasn't until Dave Hodges arrived about a year or two after the original SPICE project that the MOS transistor actually got inserted into SPICE, and we actually started learning how to make analog circuits with MOS transistors. So that was sort of the background, and it was amazing what this class project did. When the class project was done, I took on the project, the job of making this, finishing the job as my master's project. And at the time, the program was called Cancer. For reasons, and for a lot of reasons, people didn't like the word cancer. Cancer stood for Circuit Analysis of Nonlinear Circuits Excluding Radiation. And we were very proud of the fact that we built this whole program without one nickel of money from the Department of Defense, and we weren't the least bit interested in simulating radiation effects and how a circuit would work if you set an atom bomb off next to it. So we were pretty proud of that. I have to say that the name was suggested by my first wife because she walked in, we were trying to figure out a name, and she said, well, why don't you call it Cancer, because that's what it's giving you. Because I smoked a pipe at the time, and I was puffing on my pipe, and we were trying to figure out a name, and we said Cancer, and sure enough, it took. Well, Cancer didn't fly very well. We had to change the name to Spice. Or we had to change the name, and I came up with the word Spice. And that was more acceptable, and I can understand why. Although Cancer was really a lot more, excluding radiation was a lot more UC Berkeley at the time. Remember, this was free speech movement and People's Park, and we were having a good time at Berkeley. So, and then that program, I continued on that program. I was amazed at the reception. We made all of our software available free of charge. And when Don Peterson took me on as a PhD student, he said, well, one of the things that you're going to have to do if you want to graduate and get a PhD from me is you're going to have to get Barry Gilbert to like this program. Those of you who know Barry Gilbert know that he was a brilliant analog designer, maybe the most brilliant, I don't know. He certainly was a brilliant, you've heard of the Gilbert cell, you've heard of the Gilbert multiplier, you've heard of Gilbert biasing. He did an awful lot of stuff. He did not like computers. And he didn't like people who had to use a computer to design a circuit, because circuit designers design circuits. Well, after many telephone calls, I got to know Barry pretty well, and he got to know Spice pretty well, and he even started talking about how it was really, sometimes it was a full program. I graduated, got PhD, and went off to Bell Laboratories. And amazingly, the program just took off like a wildfire. People just kept coming, getting tapes of it, taking it away with them. And I think the reason it was successful, first of all, it was open source, it was free. And people, after they learned how to design analog circuits at Berkeley, they needed a tape so that they could run Spice. And it just spread out incredibly. And what's really incredible is it's still in use. And I'd like to ask, just of everyone in the audience, who has used Spice at least once? I don't think you can actually get a degree in electrical engineering from a university in this country without having to run Spice at least once. Now, who has had trouble getting Spice to converge? There we go. Okay, I want to thank everybody for this honor, and thank Brian for running the service, and this was a fantastic experience. Thank you.
Thank you very much, Larry. Before we do anything else, we want to get a group photograph with all the people who participated as speakers. If they could come up here, we're going to get a group photograph taken, and then we'll begin to do some interviews. And if they could stand next to their plaque, if they could stand so that the plaque is to their left, then I think we can get everybody up here. Yes. Oh, can you get over by your plaque? Yeah. Yeah, we're trying to get a photograph of everybody by their plaque. So do we have all our speakers up here? We have 6 speakers. We still have Ellie Harari and Federico. And let's see, is Mark Weber still here? I guess Mark Weber has left. Okay, so we've got somebody, if you can stand next to your, so that, yeah, the plaque is to your left. So, yeah, it's to your left. So if you could stand over here. And then you can stand in between your two. And then if it's to your left means you're right here. As you're looking at the audience, sorry, as you're looking at the audience. There we go. Okay, great. Can you get a full shot there, Ken? Okay, group shot. Okay, here we go. Okay, great. Thank you. Thank you, everybody. Yeah. Yeah. So I told them that you'd be the first interview. So yeah, you can catch him over there. Fantastic. He's like over there by the gear. I think he's going to be setting up his camera and stuff. Yeah. Very good, everybody. Thank you. We're done. All right. What's that? I guess that's the end of it. Yeah, turn off the mic. Sure.